Why are we having a panel about life on Mars? So each year, BC Reads selects a book to be kind of the BC book for the year, and this year it is Andy Weir's The Martian. How many people saw the movie? How many people will read the book? Okay, maybe more hands will go up after the panel. Today's event is basically the kickoff to a year of events focused around the themes in the book. And so obviously today's panel is about the challenges of getting to and living on Mars. So we have an amazing panel of experts. I'm really excited about this. We have experts in astronomy, physics, biology, environmental science, as well as engineers working in computer science and rocket engineering. So this is really exciting. To start the panel, we actually have a video from Rob Manning, who is the chief engineer at NASA and Caltech's Jet Propulsion Lab. So we will start with his short, I promise, video just kind of getting us started, okay? So thank you.
Hey Mars fans, I hope you're having a great time today at the Martian panel at Bellevue College. I'm Rob Manning. I was chief engineer for the Curiosity rover. I've been doing Mars missions and other planetary missions for many years. I'm hoping that you have a great time today. A little tell you about my background. My first Mars mission was this little vehicle called Mars Pathfinder, which landed in 1996. It bounced on airbags, and we deployed the very first rover on Mars. It's a rover we called Sojourner. It's about the size of a microwave oven. A few years later, we developed Spirit and Opportunity rovers. These two right here, you remember these? One of them, Opportunity, is still working after all these years. Can you imagine that? I don't understand how that works. And I built it. So later on, I became chief engineer for this mission, which is, you might recognize this is the Curiosity rover. Its mission was to go to Mars. In fact, it's still working on Mars, but its mission has been to understand the habitability of Mars back when Earth and Mars were both very young, and at a time when we believe Mars is a warm and wet world. So this has been a lot of fun, and we have in fact discovered that Mars was a habitable place, but we still don't know whether there's life on Mars or ever had been life on Mars. That is now Curiosity's next phase, is to look to see whether or not life might have been there. We see if we can see any signs of past life. So that's enough about me. I just want to point out that I actually grew up like most of you, grew up in Western Washington. I went to elementary school on Whidbey Island, up in Coopville and Oak Harbor, and then high school at Burlington Edison High School up north in Skagit County. So I'm from there. From there, I went to, and I grew up at a time when the Apollo missions the first astronauts were landing on the moon. I will remember that like it was yesterday, watching Neil Armstrong in this very, very grainy video, looking down at this funny angle, stepping onto the surface of the moon. It was unbelievable for us. So that inspired me. And like all of you, there's so many things going on that are very inspiring. But I want to tell you about how you might get involved in this kind of stuff. For me, I was able to get a chance to go to Whitman College in Walla Walla, Washington, where I got a Bachelor of Arts degree in math and physics. Because they had a 3-2 program, I was able to go from Whitman, taking my liberal arts education with me, down to Southern California to go to college at Caltech in Pasadena, the California Institute of Technology. This allowed me to get a degree in engineering, and I was able to take that engineering work with me when I started working here at the Jet Propulsion Laboratory, which is just a few miles away from Caltech. So that's my story, but I want to say that if you are at all interested in getting involved in science and engineering and technology, this is a great time to do it. The world really needs smart, curious people. So the kind of people we need are people like you who are curious about how things work, who have perseverance to learn things and not be too impatient, gradually do the disciplined work to find out how things work, and particularly study the core subjects, the stuff that we need for engineers and scientists. Usually are not people who are really super specialists, but rather people who are really good at the foundations, math, calculus, physics, probability and statistics, people who know how to think, people know how to ask questions, just like you. So I want to welcome you. Have a great time at this talk and this panel. This is. I wish I was there with you, but all I can do ask good questions. Do that for me. All right. Thank you. Have a great time, everybody.
So if you are interested in knowing more about Rob's experience with curiosity, since we're in the library, let me please show you can check out his book, which will tell you more about it. Additionally, Rob has agreed to do a Skype interview during the STEM to Stern class, but we will make that open to everyone, so be on the lookout for that in the winter quarter. I realized as I get ready to introduce all of you, I should introduce myself. I'm Christina Scabera, and I'm Associate Director in the Center for Career Connections, and I also run and teach in the STEM to Stern program with my colleague, Lindy Mujigira, and with Chad in the back. Unfortunately, Michael couldn't make it today. So without further ado, I'd like to introduce our first panelist, who is Dan Knight. He's an astronomy professor here at Bellevue College, and he is going to talk about Mars.
So do I talk into this? Okay. So hi everybody, I'm standing up because I have a terrible back spasm going on right now, and if I sit down, I'll never get up. So I'll just stay standing right here. So as you guys know, one of the main motivations for wanting to explore Mars is the idea that there might be life on Mars, or might have once been life on Mars. And so far, the only life that we know of is life on Earth, right? In the whole universe. And there's life in all kinds of weird places on Earth. There's life at the bottom of the ocean. There's life living in the spaces and rocks, 2 miles under the crust, and in boiling hot springs in places like Yellowstone, all kinds of extreme environments. But in all those environments, there's water. And so we think that water is a hard and fast requirement for life, at least as we know it. So NASA's mantra for looking for life on Mars or anywhere in the solar system is to follow the water. Let's see if I can do this. There we go. Oh no, I got it. It's up there. It's hard to see because it's not black. It's sort of a hard to see gray. So follow the water. Well, unfortunately, Mars is the driest desert you can imagine, right? It's drier than the Sahara. It has not rained on Mars in millions and millions of years. And not only that, it's really cold, right? It's colder than Antarctica. The average global temperature on Mars, if you average it out for the whole planet over the seasons and day and night and everything, is about 80 degrees Fahrenheit below zero, compared to the average temperature, global temperature on Earth is around 60 degrees Fahrenheit. So, there may be times when it gets up around 60 degrees, maybe 70 degrees in the summertime near the equator, that sort of thing. But overall, Mars is very, very cold and very, very dry. And also, it's a very harsh radiation environment. Mars doesn't have any magnetic field. So I don't know if you know, but our magnetic field, Earth's magnetic field, protects us from all these high-energy particles that are coming from the sun and elsewhere. So all in all, the surface of Mars is a really nasty place for life, unfortunately. Well, as you heard in the opening video, it wasn't always like that. We have clear evidence that there was flowing water on the surface of Mars in the past. There's these water-cut channels that we can see from orbit. Even ones that look just like river drainages that we have on Earth. So we know that in the distant past, Mars was warm, it was wet, there was a whole hydrologic cycle of evaporation, cloud formation, precipitation, and Mars might have looked something like this, with lakes and rivers and oceans, like 3.5 billion years ago, right? So the hope is that when Mars was nice like this, that maybe life got started, and that maybe, just maybe, it's persisted as Mars has dried out and cooled off. So, well, is there water on Mars nowadays? Yes, there is, but the vast majority of it is frozen. There's frozen water at the polar caps on both poles, and there's also water that's frozen into the ground, like permafrost. So this is a picture from the Phoenix lander in 2008, and it had this scooper arm that dug into the soil, and you can see that white stuff there is water ice. And it's not just in that one place. There's permafrost in the high latitudes, in probably both the north and the southern hemisphere. If you look at this impact crater, you see how the stuff that got blasted out looks sort of goopy, or it looks like a splatter, right? So an ordinary crater, a dry crater, or dry impact looks like this, where the ejecta is really straight and kind of stripy. But you can see in that middle picture, the heat of the impact melted the permafrost, turned it to mud, and splashed it out. Right? So we know there's frozen water on Mars. But hey, life needs liquid water. So what about liquid water on Mars today? Could there be anywhere? Well, maybe. There's a couple of places. One is there's some evidence that water might be seeping out of the ground on the sides of canyons and mountains like this. There's some controversy about what those little flow features are, but a lot of people think they probably contain liquid water. And there's caves on Mars. Yeah. Oh, okay. Well, let's make this the last slide then. So there's caves on Mars. It's kind of hard to tell what this is, but you're looking at holes in the ground. And probably there's extensive cave networks on Mars, and there could be liquid water that exists in the cracks between the rocks, hot springs, flowing water underground. And so those are the kind of places where we'd hope to someday find life on Mars if it's there. Ta-da.
Thank you so much, Dan. That was a really great introduction. And so we're sort of going to flow from Mars to how do we get there to how would we live there. And so I'm really excited to introduce one of our new faculty members here at Bellevue College, Dr. Trevor Gamble, who is going to talk with us about the physics of getting to Mars. Okay, and I will upload your slide.
So we can start with Mars, and we'll end with Earth. We can start with how to get to Mars. And actually, I pulled the idea from the book, Martian. And then we'll go to the M drive, which may or may not exist. It's an engine that it's unclear if it works or not. That's option number 2. And option number 3 is we'll talk about neutrinos, which has nothing to do with Mars, but it's a pretty interesting subatomic particle. So let's get we won't vote, but if someone shouts loud enough, we can start there. What we got? Any interest? C. What was C? What was options? What was that? The neutrinos? All right, we'll skip the neutrinos. We're going to end with Earth. All right. Boom, boom, boom. Has anybody heard of neutrinos, by the way? Can I get a couple hands? Yeah, oh, okay. All right, cool. All right, here we go. All right, we're going to skip ahead. Here we go. So first things first. E equals mc squared, Einstein's work. On the left here, we have 4 hydrogen atoms. On the right of this equation, we have the arrow there. We have what those hydrogen atoms turn into inside the sun. So this is one of the reactions that's going on inside the sun. We have smaller elements, hydrogen, and it crushes together, fusion, into larger elements. And I believe the largest element that can be created is iron. I believe that's the one. So you keep crushing it higher and higher, and at some point, you can't squeeze iron atoms together to get a heavier element. The point is, on the left side of the equation, the mass of the 4 hydrogen atoms is larger than the mass of the helium atom plus the electrons plus the neutrinos, right? So E equals mc squared. If there's more mass, m, on the left side, we have to have energy on the right side to make up for it, okay? And this is something that I learned myself. That little V sign, I forget what the Greek word for it is. Somebody help me out. What's the Greek word? Nu? Yeah, nu? Okay, cool. The nu, that's an electron neutrino. So in the sun, when it's doing its fusion thing, for the most part hydrogen and helium, it's releasing neutrinos, which shoot out of the sun I'll talk about how fast they go in a second. But that's the particle we're talking about. There's plenty of them. There's trillions going through your body right now. You don't feel it, but they are going through your body. And the most neutrinos go through the Earth and don't interact with the Earth at all, okay? So more about that. All right, Nobel Prize in 2002. This is for the discovery of the neutrino. So We have 3 people here, and essentially it was theoretically it was thought, all right, well this must be the process that's going on inside the sun. They do the all the quantum mechanics, all that good stuff, standard model, and they get an idea for what should happen. All right, well later they found evidence of, not evidence, but detection of the neutrino. So this is an old school experiment. We have a photographic plate, and you set this plate down, and when we have a neutrino that's coming on the, you see where it says invisible neutrino? It's coming from the sun. Most of the neutrinos that go through us come from the sun. Most of them don't interact with anything, but some do. So this neutrino, which was invisible to the detection plate, interacted with a proton, okay? So at the top, it knocks a proton, it kind of goes off in its little skewed path. It creates a pi meson, which is another exotic particle. Most exotic particles don't live very long, nanoseconds or something like that. They're created and then they, turn into something else. Protons, neutrons, electrons, photons, those are neutrons, those are the more stable particles. And they also, the neutrino itself travel to a pi meson or a mu meson. The words, don't worry about it. There's 100, 200 exotic particles. Again, most of them don't live very long. But the point is, you do the quantum mechanics and you figure out, oh shoot, that was a neutrino. We have this proton going this way with this energy. We have a mu meson and a pi meson. You say that had to have been a neutrino. They're very, very hard to detect. All right, moving on. So then we have 2015 Nobel Prize in Physics. So this one I like talking about. It's interesting, to me at least. So these neutrinos, they're coming in. They're hitting Earth. They're hitting we have these detectors. There's many now throughout the Earth. Many countries have neutrino detectors. And what they found was that they could only measure, well, their measurement was off by a factor of 3. They were measuring 1/3 the number of neutrinos that this says they should measure. So it's a big problem. It's like, okay, is the standard model wrong? The standard model being what we use to figure out what's going on. Is something wrong with the detector? What's going on here? We should measure a certain number of neutrinos, and we're getting about 1/3 of that. So we fast forward to the second Nobel Prize. So what they found is that the neutrinos, as they travel towards Earth from the sun, what's the word for it? They switch flavors. So if a electron neutrino is created in the sun, as it travels towards the Earth, I do the wiggly motion, it doesn't wiggle, but that's how I describe the neutrino path. As it travels towards the Earth, it changes flavors into a electron neutrino, tau neutrino, and I'm gonna go ahead and say meson neutrino. I made that up, but we'll call the third one a meson neutrino. The point is, it switches flavors. So if you build a detector that can only detect electron neutrinos, you're only going to get 1/3 of neutrinos that you should find. Okay, and that wasn't known. It wasn't known. It was a big mystery. Like, what's going on? Is something wrong with the sun? Like, what's happening? It turns out it switches flavors. You say, okay, well, that's a very strange thing for a particle to do. It changes its form. The same neutrino changes its flavor, and again, that baffles me as well. What's interesting about this is that the neutrino was thought to travel at the speed of light, right? Some people thought that, and maybe majority of physicists thought that. I'm not entirely sure there. Because the neutrino switches flavor, that means it experiences time, right? If you're changing, that means you experience time. If you experience time, you can't travel at the speed of light, because if you travel at the speed of light, anybody see Interstellar? You got a couple? All right, I won't do any spoilers, but gravity and how fast you're traveling, these things affect how you experience time. So because the neutrino switches flavor, that means that it experiences time, which means that it does not travel at the speed of light. It travels very, very, very close to the speed of light. Does that make sense? Okay, and I'll end here with, I told you I'd end with Earth. We don't cover anything here. I'm gonna go back a little bit. Oh yeah. Anybody seen this picture here? We got a couple, all right, we got a couple here. All right, what's the name of this picture? Yeah, pale blue dot. And this was taken by, correct me if I'm wrong, Voyager 1. Yes, it was the last picture that Voyager 1 took, and they turned off the camera to save energy, right? And Voyager 1 is still active now. And Carl Sagan asked if they could turn it around and take one last picture of Earth. So, we're all here, different religions and races and countries and all this good stuff. But that's us. That's us. He wrote a neat little message to go along with it. Maybe check it out when you get home, but it was a bit wordy, so I didn't put it here. All right, thank you.
Thank you, Trevor. And if you want to know more about that, then you should be taking physics, which is what we would love for all of you to do. So thank you so much. Our next guest is Kevin Weston, who is the head of avionics software at Blue Origin. And so, Kevin, just let me know and I will start the video for you.
So that's actually a great lead-in. The company I work for is named Blue Origin after that pale blue dot photo. The idea being that thousands of years from now, hopefully humanity will look back and think of Earth as our Blue Origin. So, quick show of hands. How many people have heard of Blue Origin? Okay, that's actually more than I expected, so that's awesome news. We are a company of about 850 people based here nearby in Kent, Washington, and we're working towards a vision of millions of people living and working in space. Our approach is a very gradual, step-by-step development of all the technologies required to enable that, which so far has mostly meant rockets and rocket engines. One unique aspect of our approach is that we're almost entirely privately funded. We are developing these technologies for our own purposes, which means we're not actually dependent on the government to recoup our investments. Now, before I talk about some of the stuff that we've done, let me talk about why it's relevant to the Martian. Actually, I'm going to go back one. To me, personally, if you're going to be reliably and routinely delivering people to far-flung parts of the solar system, your rockets that get you there have to have a few properties. The first is reusability, and the second is scale. So reusability is important for cost and reliability reasons. On the cost front, almost every rocket that's ever launched has been thrown away immediately thereafter, usually dumped in the ocean. These are extremely complex, tens of millions of dollar machines that we treat as disposable, single-use items. If we're ever going to get the cost of getting stuff to space and getting stuff to Mars down to a reasonable level, we're going to have to figure out how to reuse those rockets. The second reason it's important is reliability. So it turns out if you only fly something once, you don't get a test flight. Once you start to reuse them, you can begin to shake out manufacturing defects earlier in an item's lifetime before you put really expensive payloads or, God forbid, people on top of them. It also allows you to monitor and inspect the rockets after each flight. You learn more about them. You learn about the stresses that they actually endure in flight. You're getting more information and you can design better systems. The second aspect that's really key is scale. So if you've read the book, you know that every Ares mission involved tons of pre-supply missions. Each one of those is flinging tons of big, heavy stuff really far away in the solar system. Hermes, which was the main vehicle that got the people there, was constructed in space. It was a massive construction project. And again, you needed to put really heavy stuff, lots of it, in space. It turns out the most efficient and cheapest way to get lots of heavy stuff to space is to send more stuff at once. It also turns out the benefits of reusability in rockets increase the more stuff that you're sending up and the bigger your boosters get. So with that said, I want to talk about some of the work we've done. This is New Shepard. So this is a reusable suborbital vehicle. Suborbital basically means that even though it's going to space, it's basically going straight up and coming back down shortly thereafter. The entire flight is about 11 minutes, 4 minutes of which is in zero-G. This particular vehicle is designed primarily for space tourism and experimentation, educational research payloads. This vehicle made history last year when it became the first booster ever to land vertically from space. Did so again this year by being the first to be reused, and we did so 4 times. So here's more about what a New Shepard flight looks like. So there's actually 2 vehicles here. There's a booster on the bottom and a crew capsule on the top where the people would sit. They launch connected, fly to space, and separate once there. The booster re-enters first, deploys some drag brakes, which are you'll see in a minute, to slow itself down, steers itself over the pad, relights the engines, deploys some landing gear, and lands vertically. Meanwhile, the capsule's hanging out in space, providing a beautiful view to the 6 astronauts sitting inside. And then it re-enters and lands under parachutes. Here's a closer look at what actually makes this vehicle reusable. First thing, notice that this looks nothing like any other rocket you've probably seen. And that's because it was designed for reusability from the very start. It took us longer to develop, but I think that patience is about to pay off. At the top, you have what we call the ring fin. So it's a big ring at the top there. There's a gap between it and the central tank structure. During ascent, the capsule is covering that gap, so no air flows through it. But during descent, tons of air flows through it, and it stabilizes the vehicle. Before re-entry, we deploy these wedge fins, which further stabilize the vehicle. Once we've slowed down enough in the atmosphere, we deploy these drag brakes, which further cut our speed in half. And all the while, we're using these aft fins, or pivoting these, to steer ourselves back over the pad. When we're a few thousand feet above the ground, we relight the engine, deploy the landing gear, and touch down. Now, all these aspects have to work in unison, but one of the most important aspects that enable this reusability is the deep throttling ability of the BE3 engine. So the BE3 engine that powers this at full throttle, it puts out 110,000 pounds of force, but it can throttle down to just 20,000 pounds, or 18% of its maximum output. In rocket terms, that's incredible. For context, the Space Shuttle main engines could only throttle to about 67% of their max output. So, with all that said, here's a quick video that should give you a sense of the awesome reusability and landing that this architecture enables.
Five, four, command engine start. 2, 1, 0. Lift off. Your Shepherd is clear of the tower. Approaching max Q. PM confirmed separation, 250,000 feet. CC apogee, 339,000 feet. Engine is running. We have thrust. Touchdown.
When that was coming down, it looked pretty fast as it was pretty high up, but that was actually a fairly slow part of the flight. At its peak, it's coming down over Mach 3. So what about scale, the second aspect I talked about? So it turns out the vertical landing and vertical takeoff scales extremely well to large boosters, and suborbital was never our end goal. We recently announced a orbital vehicle called New Glenn. There's some pictures of it here. That New Shepard takes off with 110,000 pounds of thrust. New Glenn has 3.85 million pounds of thrust. It's designed to deliver much larger payloads into orbit and beyond. For a sense of scale, here it is compared to other rockets that are flying today, as well as the Saturn V that took the Apollo astronauts to the moon. Comes in 2-stage and 3-stage configurations to deliver a variety of payloads to different places. But that first stage is completely reusable, designed with all of our lessons learned from New Shepard, and will be flying by the end of the decade. So again, it's all about reuse and scale. We've been doing an awesome job making great progress with that at Blue Origin. We're definitely not the only ones. Personally, I'm really excited to see where we get in the next 15 years.
So the first half of the panel was really focused on Mars and how would we get there. And so the second half of the panel is how would we live there once we get there? And so I'm really excited to introduce Dr. Gordon Holgriff, who is an assistant professor in aquatic fisheries sciences at the University of Washington. And you're going to be talking with us about whole ecosystems? Okay.
I'm going to take a slightly different picture of this and turn it a little bit on its head and ask you to think, okay, if we get ourselves to Mars or any other planet, what do you need to live there, right? And one way you might approach this question and trying to figure out what you need to live on a place like Mars is to look at what you get here and what you need while you're here. And what I study is how ecosystems work, okay? So I work in a lot of places everywhere from Alaska to Hawaii to Southeast Asia. And largely the questions we ask is what makes ecosystems work? How do fish grow? What are the processes that make fish that can then turn into something that can be put on a hook and ultimately somebody's dinner plate? And how do we purify water? What are the processes that clean water such that it's drinkable? And things like that. And this is all wrapped up in the context of what we call ecosystem services. And you can think, anyone heard of the idea of ecosystem services? One? Okay, so this is the broad idea that right now on our planet, we get a ton of value, not only to us individually, but to our societies from natural ecosystems, right? We get all sorts of things just from what's out there already. And if you think about going to some other planet, a lot of that stuff doesn't exist. And a lot of it you're going to need to replace, okay? And so I'm just going to talk a little bit about those services and how they relate to human life on this planet. And while I'm doing that, I'm asking you to think, okay, now imagine going to someplace that has none of these services, none of it here. We rely on our planet in an incredible amount. So, and right now, this is a slide that's showing that, you know, we've got about 7 billion people on the planet, and they're having a pretty substantial impact on our natural ecosystems. And that's, you could have the perspective that, hey, you know, we like nature, we don't want to wreck it. But it also, you can have the perspective that we need nature in order to survive. And so you might think about, okay, look, we've got 7 billion people on the planet. We're somewhere on trajectory to end up with between 9 and 10 billion people on the planet. Some people actually use this as an argument of wanting to leave, like we're over capacity, therefore we got to go find some other place. However, keep in mind that you have to replicate all these things that we derive from our natural world that we like someplace else. So we're on track to a lot of people. People are getting wealthier around the world. So this is the amount of per capita GDP over time. So this is just an index of wealth. We're getting wealthier. And when people get wealthier around the world, they want more stuff. That generally has a greater impact on the environment right there. And then this is technology here to represent technology. And technology can cut in a couple of ways. It can reduce our environmental impact, but it also can exacerbate it. So cars certainly have an environmental impact, but we also have the ability to produce scrubbers for power plants that reduce sulfur emissions. So there's a trade-off there in what technology does to people. Any way you slice it, we're currently at this issue of we've got to think about how we're going to manage the impact on our natural world in order to preserve the services that we need and use on this planet right now. And I'll just say that I think for you folks out there, this is going to be one of the greatest challenges of your life. This is a serious challenge. We're heading to an area that is, I'm not saying the world's going to fall apart. I'm not saying the sky's falling, but we're going to have to figure out how to maintain the things that we need from ecosystems in the face of pretty substantial changes. And this is going to be something that science and smart people like yourself are going to have to think about and work on. I think water is where this is going to play out in the most obvious and acute ways, right? We use water and water systems all in so many ways. We derive so much from water. I mean, so how do we use water on this planet? Somebody throw out some thoughts. What's that? Plumbing? Is that what you said? Farming, yes, agriculture. Water for growing food, right? It's either falls from the sky for us or we pump it around and grow food off of it, yeah? Electricity, we get a vast majority of our electricity either directly from water, from like hydropower, or we use it as coolant so that we can run power plants and they don't burn up, yeah. Manufacturing, it's a base element that we need in water. I mean, water to make stuff, right? Yeah.
5.
Oh, 5 for me. Okay. Yeah, sorry. I'm getting the signal. I think she wants to talk to me, but no. Go ahead. Yeah, okay, right. So waterborne diseases is probably still the greatest health threat to human populations globally. Here, not such a big deal. Around the world, water-based diseases are incredibly important. So, I'll just throw out a little bit of information to drive this home, and one of which is the agriculture that's mentioned and kind of plant-based here, right? So agriculture represents 60% of our water withdrawal, okay? So taking water out, some of which goes back, and so withdrawal is taking the water out. Consumption is taking it out and removing it such that it can't be used again, okay? And agriculture is 60% of our withdrawal and 86% of our water consumption, okay? We use a ton of water for agriculture, right? Growing food. Hey, you need food if you go to someplace like Mars. Ergo, you need water, okay? Our traditional ways are very inefficient at using water. It's one of the main limitations. Here's another example that maybe isn't so obvious, but this is my favorite one. Is how water gets used, and this is my animal example here. This relates to the question, what's the importance of fish, and particularly freshwater fish globally? And people like to go fishing, and that's fun and whatnot, but do they matter more than that? And the answer is I think it does, and here's how I show this, is that this again is wealth. Each one of these dots is a country around the world, and this is the amount of animal protein they consume per person, okay? Not surprisingly, the wealthier you are, you eat more meat, okay? When you get money, you tend to buy things like steaks. Not surprising, we've known this for quite a while. The dots now are scaled such that bigger dots mean you get more of that protein from freshwater fish, okay? And the main point here is that if you're relatively poor, you go and get your protein from the little stream and creek and lake behind your house, okay? And that's incredibly important for people in relatively poor parts of the world. They're already low in the amount of protein that they get, and where they get it directly from natural ecosystems. This is an ecosystem service that they derive right there. And so now think about, if we go someplace else, we're gonna have to think about how to replace some of this stuff. Fish is probably not what we're gonna be growing on Mars, but think about all the ways we use natural ecosystems to benefit people. That's a hard thing to replicate. Yeah. Yeah, so general meat consumption, with the exception of fisheries in most cases, not all, but is highly dependent on water through agriculture, growing grain to feed to cows. Exactly, yeah.
Okay, thank you. And just a reminder, I know that these are brief presentations. The goal is to really get you to then follow up with each of our experts afterwards. There will be lots of time for you to ask them questions. So recognize that these are brief, but we really want you to chat with them afterwards. So our next guest is Dr. Roshni Tiwari, who is a biology professor here at Bellevue College, and she's going to talk to us about agronomy, which I know very little about, and I'm excited to learn more.
All right, who can define agronomy? Oh, do I need this? Yes. Okay, for the TV, sorry. Who can define agronomy? It is agriculture, but it's just crops, so it doesn't involve fisheries, it doesn't involve animal husbandry, it's just growing plants. And so my specialty is agronomy, so my first degree was in general agriculture, then I specialized in plant sciences, and then for my PhD I specialized in legumes. And agronomy is a very broad topic, but basically we're trying to study plants. And where do most of our plants grow? In the ground, that's right. So we need something to grow it in. We need soil to grow it in. So we do our studies there. Yeah. Oh. Yes. Okay, so we're trying to study plants. Okay, so I decided I would talk about agronomy because not many people have heard about agronomy. And then I'll talk a little bit about growing plants elsewhere. So it's a study of crop plant growth, and it requires our knowledge of plants and soils. We need to know what a plant needs to grow ideally and grow well and grow efficiently and effectively. So these are some of the areas that agronomy covers. We work on edible plants, and then we also look at the most common edible plants as well. We're always trying to figure out what plants will become more common and consumed, but most of the research is done on the common ones. And we also try and do research on how do we grow something in really poor soil. So that can kind of mimic what's going on, you know, if we try to go grow plants on the moon, or if we try to go Mars on Pluto, and nobody's, okay, Mars, not Pluto, not just yet. Give us a century or two. Okay, so growing plants in soil and amending that soil so we can grow the plants. Where can we grow plants? Okay, where can we not grow plants? There's a question I have for you guys. In the water? Well, yeah, that's true. Underwater, well, we could grow plant-like organisms. In the Arctic, actually, we can grow plants in the Arctic. We can grow them anywhere because we are awesome. We're humans and we just modify everything. Okay, so we grow plants in soil-like medium. We grow it in aquaponics. And we try and think about what nutrients that we can provide so we can grow them anywhere on the planet. And so what we have to do is we have to regulate the environment for plants. So we have to think about the sunlight, the UV light, temperature. But if we're growing to, so we can sell the food, we also have to think about payback. We have to make sure that how much ever money we're putting in, we can make that in profits with what we're trying to sell. All right, so there's always a limitation to what we can grow. And we don't often think about food. I mean, students don't often think about growing food, but they do think about eating food, all right? And then, although if there was a big storm, and most of you were running to the grocery store to get batteries, to get water, and also to get food, yeah, hopefully food, yes, or something like food, okay? All right, so drought, storms, hurricanes, wars, these are when we think about food or going to Mars. Because if you get to Mars and you have a lot of water and you have all the air you need, but you don't have all the food you need to survive, it doesn't matter that you could have everything else. So what do we need to modify our environment? And this is stuff that we've been using for centuries. We can modify a lot of environments to expand how long we grow a plant, figure out when we're going to get it to flower. So we use greenhouses and we manipulate, the environment so we can grow plants anywhere. We manipulate it so we can get Easter lilies at Easter time, but Easter lilies actually like to flower in the summer. They don't like flowering at Easter, but we force them to because you can sell them for lots of money, right? So we can manipulate plants, so we can grow them. This is lettuce that was grown in space. And we've been trying to grow in space since the 80s, so it's not really a recent phenomenon, but it's something that we've been studying for a while. But it's really hard to mimic space on Earth, right? Because you have things like gravity that you can't avoid. You can pretend it's not there, but it's always there. All right, so this is lettuce, and they tested it to make sure that it was safe for people to consume. And they found out it was safe. So last year, NASA posted a slide of them sharing with lettuce and eating the lettuce. I think they had to also clean the lettuce. So we have a few questions. Can we grow plants in space? What plants should we grow? And what do we need for them to grow? And the other question that we have is not just can we grow them once, is can we grow them indefinitely for multiple generations again and again and again? Okay, so areas of study, I do have one error in here, but just ignore that. Just ignore all my errors. Okay, so areas of study, we want to think about the control conditions. If you're growing in space, you're essentially going to be growing in a greenhouse. You want to make sure the plant's getting enough oxygen. You want to make sure the temperature is right. Oh, 5 minutes, sorry. You want to make sure it's not too hot, not too cold, all of that stuff. The other thing is you want to figure out how to grow plants when there is a different kind of sensory mechanisms that they're responding to. So if there's no gravity, how do they grow? And they found that the other trophic effects, which is the response to light and the response to water and the response to nutrients, also influence plant growth. And so the plants can grow a decent amount. We do have some impact on the different proteins that they're expressed, but the plants' proteins are expressed that they're stressed. If you were in space, I'm sure you'd be stressed, you know? So the plants are also stressed in space. We want to make sure they're nutritious for us. We don't want to assume that if we eat lettuce here, it's going to be just as nutritious elsewhere. So we have to test that. The microbes, you may think of the International Space Station as being really clean, but you know, we bring bugs with us everywhere. You know, think about your GI tract. You're just a body of bugs just walking around with some human cells. So we got a lot of bugs in you. And we want to make sure that if you're growing plants that, you know, the bugs that do get on the plant are healthy for you. We want to think about the light spectrum. So down here, our atmosphere filters out the UV light to some extent, but if you're growing it on Mars, you have to think about filtering out that UV light, which can be damaging. And then you also just want to think about, you know, all the other safety issues that I may not have covered here. So these are just some areas of study that I brought up. And I'm done. Good. Thank you. Bye.
Thank you. Just as I moved to the mic, you sensed it. So I'm really excited to end the panel with my friend, Brian Swindell. Now, I invited him for a number of reasons. First, he is a fellow University of Arizona graduate. Go Wildcats. We're waiting for basketball season. For all the UW fans, football's going great for you. Basketball's more our thing in Arizona. Brian is a graduate from the U of A's computer science program, but I invited him because he is a bit the Mark Watney of the group. That's the lead character, for those of you who haven't read it yet. Brian is here to actually talk about the greenhouse that he built in his backyard and actually has programmed to run. So, Brian, I will get your slides for you.
This is such a cool event. I'm so excited to be here. So, like Christina said, my name is Brian Swindell. I'm less of an expert than probably the rest of the experts on our panel, but hopefully my project is a little more relatable to the STEM students that we have in the audience. Let's see. So I'm talking about automation in agriculture, how it applies here on Earth, and things that we can do with it in a Martian environment as well. So a little bit about me professionally. I'm a software engineer. I work for Amazon.com. I've been there for a little over 3 years. Before that, I worked in the aerospace industry for a couple of years. As a hobbyist, I like to grow plants using as much technological intervention as I can. That's a cool term for just automating things. So when I was in college, one of the cool things I did was some work at the Controlled Environment Agriculture Center, CEAC for short. CEAC is a really cool facility where they have some commercial scale greenhouses. We grow a lot of peppers, tomatoes, cucumbers, and we churn them out on a weekly basis, and we give that food to the student union restaurants. It was a really cool project to be a part of and to see how modern technology can make farming so efficient. Another cool thing that the university does is they work on, they're actually affiliated with NASA, and they work on the Mars missions. They work on the rover right now, the Curiosity rover. And so part of the NASA grants that they get actually goes towards things like this lunar greenhouse that you see in the top right there. So this is essentially a modular pod that they can deploy to Mars or to the moon and grow plants hands-free. The leaders from the SEAC actually did a Reddit Ask Me Anything about the Martian, so that was one thing that's particularly relevant for this panel. They consulted with the film producers, and they also had some cool kind of debunking on things that happened in the movie, if you want to take a look at that. So my greenhouse in my backyard was a lot smaller. I was inspired by the things that I did in college. It's about 8 feet by 6 feet by 8 feet. All of the stuff that I used in there I got from Amazon. It was about $600, but if I was to do it again, it would come out a lot cheaper. I grew a wide variety of peppers, and there's a lot of cross-discipline sciences and engineering involved, from a lot of the computer science skills that I'm good at, some green thumb skills that I'm pretty bad at, some chemistry in terms of the hydroponic stuff. Pest management was something that was actually really tricky, and it's a lot different to deal with probably on Mars. You see in the bottom left picture, that's a deep water culture hydroponic system. That's something that Dr. Tawari just described. It's growing plants without soil. The roots are just suspended in a nutrient solution where, as long as you're providing oxygen and nutrients into the water, they don't need soil. The one next to that is actually an aeroponic system. It's really efficient in terms of water usage. You actually spray the roots. The roots are just dangling in air, and you spray them on a timer. I do it every 15 seconds out of every 2 minutes. Let's see. So the stuff that I'm good at. So in order to automate the things in there, the platforms I was working on are the Raspberry Pi and the Arduino. So Raspberry Pi is it's like a $20 Linux computer. If you've never seen one, it's about the size of a wallet. It has USB ports. It can connect to Wi-Fi. You can do all of the things that a personal computer can do. You program it in high-level ways, so I programmed it. The programming I did was in Python. And it's kind of the brains of my operation. The Arduino is more like the eyes and the ears and also the hands. It's a microcontroller. The one I use cost about $12. It's actually responsible for picking up the analog signals from the greenhouse. So this is like temperature, humidity, light, giving that off to the Raspberry Pi to make which runs the business logic, and then the Arduino also connects to different electronic loads to turn on a heater or to turn on a fan or to turn on a light if needed, stuff like that. So yeah, the Raspberry Pi is kind of the brains, and the Arduino is kind of the limbs and the eyes and the ears. Here's a little diagram that I drew to kind of illustrate how it all works. There's a master-slave relationship between the Raspberry Pi and the Arduino. Those are the two rightmost columns here. So the Raspberry Pi actually commands the Arduino to give it readings. The Arduino follows the commands. The Raspberry Pi might tell it then to turn on a light or to turn on a heater or to turn off a heater. But the other thing that it does, which is the reason why I chose to program on 2 computers instead of 1, is that the Raspberry Pi can log these things over the network to all of the data that it processes. It can log to a network shared drive. And the cool thing about this is that I can then access it anywhere over the internet and make changes to the system in real time, even if I'm at work or if I'm across the country. So here's some of the data visualization that I was talking about. This is the data that I logged from July 24th, so just over 3 months ago. The yellow line corresponds to light, and when I look at that, it makes me really miss the summer. You see the sun rising at about 5, so it's setting at about, 9 o'clock. Green is temperature. That's going up into the 80s there. Red is humidity. These are pretty ideal conditions for growing peppers, which is what I was growing. Compare that to 3 months later in October, much less ideal conditions. So a lot less sunlight when you compare the two, for one. Temperature is also much lower. That's the green line. And you see the spikes going up and down. That's the heater turning on and off, which is the logic that I had programmed in there. Just barely getting it up into the lower threshold of where my peppers wanted to be. So there are some differences growing on Earth versus growing on Mars. I think foremost, one of the things we talked about is how different of a climate Mars is in terms of dry and cold. So that October graph that I showed is pretty undesirable by Earth standards, but that would be like a great day on Mars. Dr. Tavari also mentioned gravity is something that we experience on Earth that's really hard for us to not experiment with. We talk about managing resources in terms of water, electricity, nutrients. Mark Watney had to use his own biological waste material as fertilizer. I didn't have to do any of that, thank goodness. So there's a lot more constraints growing on Mars than growing on Earth, but you can apply the same lessons. As you get really good at these things on Earth, then that's kind of when you're ready for prime time and take stuff like that to Mars. That's it.
Sharing the photos from your awesome greenhouse. So initially I was going to ask the panelists a few questions, but I can see people are very anxious, I think, to chat with them and ask them about their work. So what I'm going to do is, first of all, thank the panelists one more time for being here.